All right, problem of the day number 9 was a chance for you to practice your synthesis problems. I noticed on the exam that was where a lot of people tended to struggle, was planning out a synthetic route. And so I'm going to try to incorporate it into a lot more of the pods coming up, including our synthesis days on Thursdays. But let's go through this pod. And the most important thing when you're planning a synthesis is to plan one step at a time backwards. We have 2 different ways of making ketones. One is ozonolysis of alkenes. What's the other way? Yeah, acid catalyzed hydration of what? An alkyne, exactly. So if we look at this, we have to plan our alkyne. And I'm going to draw out a couple different alkynes. So 1, 2, 3, 4, 5, 6, 7, 8. We could have this alkyne, or we could have this alkyne. Which one is the preferred alkyne for the acid catalyzed hydration, and why? The right one. Why is that?
That's how I did it.
Because that's how you did it? That's a reasonable explanation. Does anybody have a more elaborate explanation? Yeah, what was your idea, Tim?
It's going to be the same on either side.
Yeah, exactly. So if you go back to your chapter 10 notes on alkyne hydration, I told you that if you have an unsymmetric internal alkyne and you do acid catalyzed hydration, you'll get 2 different products. In this case, we only want one product. We don't want to lose a bunch of it. So if you are going to do this, it'd be preferable to use the symmetric alkyne shown on the right. All right, what reagents do we need? Acid, right? So H2SO4 and water. And what else? HgSO4. We need a catalyst because the activation energy is very, very high. And remember, when we do this, we form an enol that undergoes acid catalyzed tautomerization, and so you should be familiar with the tautomerization mechanism for this. All right, now the question is, well, how can we make this internal alkyne? If you look at the directions, I tell you guys, you have to start with organic building blocks containing 4 carbons or fewer. This one has way more than 4, so we've got to piece it together. What ways do we know of adding carbons?
Yeah, well, you can use NH2.
Okay.
Then you can use some 2-methyl propane with like iodine or something.
Okay, so let's try just tagging on one of these ends onto an alkyne. So let's do this. We're going to have this terminal alkyne, and we're going to treat it with an electrophile that has a leaving group off of it. And is that all I need? We need a base first, right? First thing we have to do when we're doing this is to deprotonate our terminal alkyne and then react it with our electrophile. So step 1, we could have NaNH2 or any suitably strong base. Let me slide this over. And then second step, we'll treat it with this electrophile. Let's go back to that electrophile in a second here. But let's take one step backwards and say, well, how can we make this terminal alkyne? It's pretty similar, right? We can start with acetylene. We can deprotonate it using a suitably strong base. And then treat it with that same electrophile. So now we've got building blocks with 4 carbons or fewer, but let's try to be fancy. And let's show how we're going to make this building block. So what's one method we can use to make this building block? Yep, so there's a couple different ways. Let's do both of them. We could do the easy route and treat it with an alkene and do anti-Markovnikov halogenation. That would be one route. What if we want to start with an alkane? Ah, yes. Now we know how to functionalize our alkanes. So we could do Br2 and UV light. Now, how can we continue on? We've got the bromine coming off of the more substituted carbon, but we need it coming off of the less substituted carbon. E2 elimination. Okay, so we could do something like sodium ethoxide. And then we can do the same thing. We can do our anti-Markovnikov. Yeah, but the thing is, this is really good practice for reviewing reagents that you need, regiochemistry, and so on. Oftentimes, there's more than one route for a chemical synthesis. You normally default to the easiest route, the route that's cost-effective and the route that's greenest. But oftentimes, it's good mental exercise to go through and try to do it as many different ways as possible. So that's excellent practice. If you are struggling with synthesis or just simply want to review chapters 9 and 10, I would recommend doing as many book problems from chapter 12 as possible. It's excellent review of chapters 9 and 10 and 11. And it teaches you good strategies for planning out synthesis problems. All right, are there any questions with the pod? No? Yeah?
I just say a question. So, like, usually I use iodine for the clamping, the clicking on parts. Is bromine always the preferred for everything? Or?
It's a lot easier to brominate molecules than it is to iodinate a molecule. Oftentimes the carbon-iodine bonds are so weak that they're very reactive and tend to fall apart, where a carbon-bromine bond is a little bit more rugged. It's easier to make.
Okay.
Yeah. All right, so let's go back to our alcohol chapter. And let's review a little bit of what we covered yesterday. Yesterday we said we knew of a few different ways to make alcohols. The first way we covered last term was through SN2 or SN1 reactions, and that depends primarily on your nucleophile and your electrophile. And then in chapter 9, we covered addition reactions of alkenes, where we can treat an alkene with acid, or we can do hydroboration oxidation, or we can do oxymercuration demercuration. So all three of those routes can be used to make alcohols. However, we covered a couple different ways too. And I want you guys to help me fill in these reagents. The first one creates two new alcohols that are on the same side. What reagent would we need for this? Yeah, osmium tetroxide, the reagent that will make you go blind. And then what do we need in the second step? Yeah, you can use NMO or NaHSO3, sodium bisulfite, and water. You need some sort of reductant in order to form your syndiol. All right, the other one that we had creates a mixture of enantiomers where the alcohols add anti to one another. What reagent do we need for this reaction? MCPBA for the first step. And then the second step, what do we need? Yeah, we need some sort of acid, catalyst, and water. All right, so we already know a variety of different ways to make alcohols. These will come in very useful for synthesis problems in chapter 13, but I did want to take a second to review them. Now we get to go back to Gen Chem stuff. Are you guys excited? Yes. Yeah. You rock Gen Chem. All right. We're going to do a little review of Gen Chem. There's some people that haven't taken Gen Chem in a few years, so I did want to brush up on this. All right, reduction. Gaining electrons. Oxidation. Whoops. Is losing electrons. So there's a variety of mnemonics you can use. In case you forgot them, you can use oil rig or Leo goes grr. Whatever one works for you, just try to remember this. You'd be surprised how many chemists forget basic oxidation reduction chemistry the further along they get in their careers. So let's cover oxidation state. And compare it to formal charge. How many of you guys covered oxidation states for carbon atoms in Gen Chem? A few of you guys? I know some classes don't go over it in much detail, so I did want to briefly review it. So let's say we've got methanol, got H3COH. What I typically do when I'm trying to determine the oxidation state is I draw out all of my electrons. So we've got a covalent bond here to hydrogen, covalent bond here to another hydrogen, covalent bond here to another hydrogen, covalent bond to an oxygen. That oxygen has 2 lone pairs, and it's bonded to a hydrogen. So now we've accounted for every single electron. The rule for determining oxidation state is the more electronegative atom gets all of the electrons. When determining oxidation number. All right, so if we look at methanol, what's more electronegative, carbon or hydrogen? Carbon. So if we look at it, carbon's 2.5 on our table, hydrogen's 2.1, so that means carbon's going to get all of these electrons. And what's more electronegative, oxygen or carbon? Oxygen should be. So if we look at oxygen on the table, it's 3.5, carbon's 2.5. So in this case, when we circle all of the electrons that belong to carbon now, we're going to circle all of those. And the way to determine oxidation number is you do the valence number minus the circled electrons equals oxidation. So in this case, what's the valence number for carbon? Okay. Oops, shoot, where'd it go? So we've got 4 electrons as its valence. How many circled electrons? 6. So its oxidation number is going to be -2. What's the formal charge of the carbon there? 0, right? So formal charge tells you whether or not it's an anion or cation and what the charge is. But oxidation number is entirely different. It tells you how many electrons are closely held by a specific atom. And in organic chemistry, we're primarily dealing with carbon atoms, and we're looking oftentimes at oxidation or reduction of various sets of carbons. All right, so let's do another practice one. Let's do C2CCH2. So we've got ethylene. I want you guys to tell me the oxidation number of the carbon. Either one. And I'll give you guys a hint too. If there's a tie, so if tied, then share. So if you have the exact same electronegativity, then you have to share those electrons between 2 atoms. So let's draw out our electrons. I know this is going back to Gen Chem a lot. It's good practice. All right, what's more electronegative, carbon or hydrogen?
Carbon.
Carbon. What's more electronegative, carbon or carbon?
Carbon.
Trick question. So the carbons here are equally electronegative, so one won't win out, so they're going to share electrons. So we actually only circle half of those, and we can steal all of those electrons from hydrogen. So again, we'll do the valence number, which is 4. This time we've got 6 electrons, so 4 minus 6 is again -2. So the oxidation number of both of these carbons is -2. All right, so now let's go into redox chemistry with organic reactants. And let's do this example from chapter 9. Let's say I've got acetylene, and I want to go to the corresponding alkane. What reagents do I need? Yeah, H2 and platinum. So a catalytic hydrogenation. All right, now let's determine the oxidation number for our starting material and our product. And I'll draw out all our electrons. There we go. So what's the oxidation number going to be for this carbon on the left?
-1.
Okay, so let's go and double check. Carbon's more electronegative than hydrogen. And these two carbons are shared, so we've got 4 minus 5 equals -1. Perfect. So the oxidation number of a carbon in an alkyne, at least this alkyne, is -1. If we look at the carbon on the right, we again have a carbon-carbon tie. Carbon's more electronegative than hydrogen, so we do our valence number, which is 4 minus 7. So we've got -3. All right. So did we gain or lose electrons? Gained electrons. So we gained 2 electrons. So is this an oxidation or a reduction reaction? Reduction. Is this similar to how you guys were taught in Gen Chem? No? All right. I'm glad we're reviewing this then. So oftentimes in organic chemistry, we'll refer to a reaction as an oxidation or a reduction, but we're not looking at metals with charges. That's probably what you guys saw a lot in Gen Chem, right? Was you were looking at charges of metals and trying to compare whether or not they were going up in charge or down in charge. Now we're looking at carbons, so we have to follow these really specific rules when we're determining oxidation number. Let's do another one. All right, for this one, we're going to do acetophenone to a secondary alcohol. And the carbon in particular that's being changed is this carbon right here, and it got changed into an alcohol. So let's try to determine the oxidation state of each of these carbons and determine whether or not this is an oxidation reaction or a reduction reaction. And I'm just going to draw in the benzene ring because we know that that's going to be unchanged in this reaction. There we go. So I'm kind of using some shortcuts, just showing the electrons that are covalently bonded to the carbon we're interested in.
Didn't you do the right or wrong? It's not no.
Oh, sorry. Thank you. Good catch. This is why I keep you guys around. Just kidding. I like you guys. Here we go. So now we've got our secondary alcohol. We have to remember that assumed hydrogen. All right, what's the oxidation state for the carbon on the left?
-2.
So yeah, let's take a look at this. The oxygen's more electronegative, so that carbon doesn't get any of those electrons that are bonded to the oxygen. However, there's a tie between those two carbons, so it has to share those. So we have 4 minus 2, which is actually positive 2.
Oh, I looked at the oxygen.
Yeah, so in this case, we have to specifically look at the carbon that's reacting, not the oxygen. We could do the same thing for the oxygen if we want, but we're organic chemists, so we're primarily interested in carbon. Let's do the same thing over here. Now, carbon's more electronegative than hydrogen, so it will steal both of those electrons. It'll only get half of the carbon-carbon electrons. And now we've got valence number of 4 minus our 4 circled electrons, which is 0. Does that make sense? So did we gain or lose electrons? Gained. So this would be a reduction. What do you think happens if we go from an alcohol to a ketone? Be an oxidation. So quite often we'll learn these as pairs, where I'll show you a reduction reaction, and then I'll show you the opposite reaction that will be the reverse of that. Yep?
How do we know which carbon we want to
Typically it's the carbon that's been reacted. So if we look at the benzene ring, we haven't added or removed any atoms from there, so they were untouched. Same thing with this methyl group coming off the end. It's a methyl group in either case, so there wasn't really any chemistry going on there. Yeah, so we want to look at whatever carbon has new bonds associated with it. All right, so now let's go into reducing agents for chapter 13. Yep, this is alcohols are in chapter 13. So let's do reducing agents. For aldehydes and ketones. All right, there's one reaction they love to show in your book, and so I'm going to present it, and then I'm going to tell you guys to ignore it. Platinum, palladium, or nickel. And they say if you do this, you can reduce the double bond to a single bond, just like we saw with alkanes. And they say, all right, if you do this, you can get to an alcohol. However, I'm going to put an asterisk in here, and I'll say, no one does this. Why do you think nobody does this?
It's expensive.
It's expensive. What if you have an alkene in your starting material? You'll also reduce your alkene too. So this is a really non-selective reaction. It requires extreme pressures that are oftentimes very dangerous, and chemists prefer to avoid pressurized reactions at all costs because it's just a pain to set up and you don't like things exploding in your lab. So instead, I'm going to show you guys an alternate technique that doesn't involve high pressure systems. And specifically, we're going to use the same ketone. And in this first reaction, we're going to use a reagent we've already seen, NaBH4. Does anybody know the name of that? If I mutter slowly enough, they'll think I got it right. Sodium borohydride. So in this case, it's a hydride source. What's hydride? H minus. It's not H plus, it's a deliverer of H minus, so hydrogen with electrons. Oftentimes these are run in alcohol solvents, and when you do this, you can form a secondary alcohol. Oop. Why do we call this a secondary alcohol? What we do is we look at the carbon where the alcohol is attached, and we ask ourselves how many other carbons are attached to that point. So in this case, that carbon is attached to 2 other carbons, so we call this a secondary alcohol. All right, let's do the same sort of reaction with aldehydes, and then predict what our product might look like. What do you think the resulting product will be if you treat an aldehyde with sodium borohydride?
Primary alcohol.
A primary alcohol, right? So if we look at this, we can still reduce out here, but now we just formed a primary alcohol. All right, let's do something a little bit different. Let's say we want to get our tertiary alcohol. What would our starting material have to be? Not both. I'll give you a hint. It's kind of a trick question. If you look at the top 2, that carbon-oxygen bond in our alcohol used to be a carbon-oxygen double bond. So if we tried to do the same thing here, which I see organic chemists try to do once in a while, you have this as your starting material. What's the problem with this? Texas carbon. So in this case, we can't make tertiary alcohols using this sort of reduction. We can only make primary and secondary alcohols. All right, so now let's go through the mechanism for this reaction, which is not too bad, but looks a little bit different. First part of the mechanism, I always like to draw dipoles. That way we can figure out where our electrophilic site and where our nucleophilic site is. And we've got sodium borohydride, so it's boron with 4 hydrogens. This boron has a negative charge. And we've got sodium as the counter cation. What I'm going to do is I'm going to change one of these hydrogens to blue, just so we can keep track of it. But before we do any sort of arrow pushing, let's identify our dipoles. So in our starting material, where's the net dipole? Yeah, it's pointed up towards the oxygen. Oxygen's far and away the most electronegative. So we've got a really nice dipole there. In this case, what's going to be the electrophilic center? Is it going to be the carbon or the oxygen? The oxygen. So let's step back. What's going to be the electrophilic center? The carbon, because the carbon has that partial positive. That means it wants electrons. Sorry about that. So what will happen is this will steal a full hydride from the sodium borohydride, and then we have to break one of these electrons and dump it up to the carbon. Oxygen. Sorry. I'm getting all tongue-tied today.
So you want your arrow pointing from the hydrogen?
Yeah, you want it from that sigma bond between the hydrogen and the boron. Okay, so this oxygen now has a negative charge. We've got a CH3, and then we've got a new hydride that's attached. All right, what do you think the last step is? Not quite. If we go back up and we look at our answers, If you notice, the final product didn't have a charge on it. So we've got to do a proton transfer. And in this case, I told you guys, typically this reaction is done in an alcohol solvent. So this can steal a proton from the solvent, dump down onto oxygen, and now we get our final product.
So H2O would be equivalent to it? H2O.
Typically, people will do this in an alcohol. Water tends to slow down sodium borohydride, although I have seen reactions where you can use water. It's just not common. So typically, you use an alcohol instead of water. And there we go. We always call this our borohydride anion. And it's always going to deliver a hydride or an H- during one of these reduction reactions. Does that make sense? All right, so let's continue on and talk a little bit about reducing agents for other carbonyls like carboxylic acids and esters.
I have a question.
Yep.
That when it comes to H3, is that now a signal planar that can really do stuff in the reaction if you're not careful, or?
Yeah, once it forms borane, BH3, then it can be a good Lewis acid and can coordinate with lone pairs. But in this case, it won't stop the reaction. It'll just keep on going.
Okay.
Yeah, it'll typically be tied up by the alcohol after it does the reduction. It kind of comes down to competition. Because you're in a sea of solvent, it'll just coordinate with the alcohol and be inert after that. All right, so let's do the reducing agents for our other carbonyls. So reducing agents for carboxylic acids and esters. All right, so let's take a look at an example of one of these. And for the example, I'm going to use an ester. This time, if we reduce it, we're still going to form an alcohol. However, it's going to be a little bit different. So this whole portion on the left-hand side will become one alcohol. And then this whole portion on the other side, let me actually do that in a different color, will become a new alcohol. So we can essentially cleave esters into their individual components when we do this reaction. The reagents required for this are lithium aluminum hydride. So Li, that's for lithium, Al for aluminum, and then H4. And then in step 2, we have to add in water. Oftentimes, you'll see people abbreviate lithium aluminum hydride as LAH. As LAH. So that's just short for lithium aluminum hydride. So let's take a look at this reaction mechanism. Again, it's pretty straightforward, but it's got a little bit of a twist from the last one. All right, so I'm going to use that same starting material that we had drawn on top. This time we've got aluminum with 4 hydrogens coming off of it. What do you think the first step in this reaction is going to be? We've got a big dipole. Yeah, exactly. The hydride, just like we saw before, will attack that central carbon on our carbonyl. It's going to kick up electrons onto that oxygen. Now we've got an oxygen with a negative charge. We've got a OCH3 group on there still. And we've got this hydrogen. All right. If we look at this, it doesn't quite look like the products we're getting out of the reaction. But what do you think that negative charge can maybe do? Yeah, it's a little bit like resonance, but in this case, if we try to push this down, we would form a Texas carbon. But we've got a fairly good leaving group there, right? If we look at this guy over here, we could eject it off. So in this case, this will kick off an alkoxide anion. And now we have an aldehyde plus the other end of our ester, which is now an alkoxide anion. Okay, now that we've got this aldehyde formed, it will immediately react with another equivalent of lithium aluminum hydride. So let's draw in our second equivalent. Oops, sorry, I forgot my negative charge on the aluminum. And what do you think the next equivalent of the lithium aluminum hydride will do with the aldehyde? It'll do that same reaction, right? So this hydride will attack that central carbon. It will kick up electrons.
How about the other side? The OCH3 is there?
So right now it can't really do much but hang out as the anion, but we'll come back to it. Okay, so we've got this aluminum hydride attacking in. Now this oxygen up here has a negative charge. We've got two hydrogens attached. And let's not neglect this guy. This one's still floating around in solution, the other alkoxide anion. And what do you think the last step will be? Similar to the last reaction. Yeah, exactly. We need to do a proton transfer. So if we look at this, we can say, all right, in the second step, we had water. And so each of these alkoxide anions can grab a proton from water, and we'll end up with,
I thought I said water was not good.
this is a new reaction. So water was listed as the second step in this new reaction. All right, I've got a question for you guys. In the sodium borohydride reduction, we ran it all in one pot with alcohol as a solvent. This one I very clearly indicated step 1 was add your lithium aluminum hydride, and then step 2 was to add in water. Why do you think I broke it apart into steps? It matters. Why do you think it might matter?
That would happen at an undesirable time.
Yeah, let's take a step back and think about hydride for a second. In this case, we had hydride acting as a nucleophile and doing a reduction. What else is hydride good at? Acid-base chemistry, right? So we saw sodium aluminum hydride in a lot of acid-base chemistry. In this case, we don't want the lithium aluminum hydride to do acid-base chemistry, so we have to separate out the steps. Based on that, which reagent do you think is more reactive? Lithium aluminum hydride or sodium borohydride?
Lithium.
Yeah, lithium aluminum hydride is really, really strong. So let's make a note of that. That means we must do deprotonation, or sorry, protonation. Separately. So that's one important thing. Do you think lithium aluminum hydride would work on aldehydes and ketones? If it's really strong?
Yeah.
Yeah, it could work. So this will also work with aldehydes and ketones. I had a student last year who got kind of fed up with this, and he's like, well, why do we need to remember 2 reagents if one will do the job for all 4 of these functional groups? And the analogy I used to give him was it's like trying to hammer a nail with a sledgehammer. It's overkill, right? Oftentimes as a chemist, you don't need to use the most expensive, elaborate reagent that's really reactive and difficult to handle if you can avoid it. You want to use the gentler, easier to use reagent. So typically with these reactions, when you see a reduction of an aldehyde and ketone, you use sodium borohydride. And when you're looking at a carboxylic acid or an ester, you use lithium aluminum hydride. So that's one important difference.
What is the lithium doing? It's only the mechanism.
So the lithium in this case plays an important role with the carboxylic acid reduction, which we're going to actually leave until chapter 21. So we'll talk about that more, but lithium coordinates with the oxygen and actually helps the reduction occur. So that's a little bit outside of the scope of this section of the book. Does that make sense? The pod that I gave you guys involves a mechanism. What functional group is present in your starting material? Ester. So if you noticed, I used lithium aluminum hydride as your reducing agent, and I want you to show stepwise every single arrow, every single lone pair going from your starting material all the way to your product. Does that make sense? All right. So those are the 2 main reactions for this section in the book. But let's go to the section on diols really quick. Diol is just short for something with 2 alcohols. And we've already reviewed a little bit on this, but I just wanted to reiterate that we already know 2 methods of making diols. We've got one where we can make cis diols, or syn-diols, I should say. And then we've got one where we can make anti-diols. And the top one, we said we need osmium tetroxide, followed by sodium bisulfite and water. And the second one, we need MCPBA, followed by acid and water. So we already know a couple different ways to name these. But one thing I did want to get back to was naming for these. There's a couple different ways to name diols. I'm only going to briefly touch upon this. And we're going to use one of the most common diols. It's found. Yeah. This diol is coming off of a 2-carbon chain. So what do you think the parent name is going to be? Eth, okay, or ethane because it's a alkane. And if we try to number this, we can say, all right, we've got 1, 2. Oftentimes you'll see this written as 1, 2 ethane diol to indicate that we've got 2 alcohols coming off of the 1 and 2 position. There's also another very common name for this. Oftentimes people will call this ethylene glycol. So if you look at the suffix glycol, this is really just a pseudonym for a diol, right? So a glycol is two alcohols adjacent to one another. Why do you think we call it ethylene? I actually saw this on a chemical forum on the internet the other day. People were like, why are they using the ene suffix if it's an alkane? It's an important question. So if you look at ethylene or methylene, what it's really in reference to is a CH2 group between two things. So it's ethylene because it's between two things. Methylene would just be a CH2 by itself in between two substituents. So when we talk about methylene chloride has two chlorines coming off of it. And it looks like this, but the methylene is just in reference to the spacer right there. So it's one CH2 unit, so it's methylene. Two would be ethylene. We can have propylenes and things like that. So that's one thing that threw a few people last year, but I just wanted to go back and point out that ethylene doesn't mean that there's a double bond in there at all. Does that make sense? Yeah, it's found in antifreeze and a lot of commercial products, although it's being phased out because we found out that there is some liver toxicity. Fun fact, I found this while I was working. Oftentimes when you get an MSDS for a form or for a chemical, it tells you what to do in case of ingestion. This causes really bad liver problems. Does anybody know the solution to it? Yeah. Yeah, you have to chug a bunch of vodka, essentially, to try to...
Strong vodka.
Yeah, exactly. It was one of those things where I was like, should we have vodka in the lab then? Like, it's for safety, I guess. But essentially it overwhelms your liver and prevents your liver from metabolizing this. All right, I think we're going to pause right there. Make sure with your problem of the day that you guys seek out help if you need it. Try not to leave it until 10 minutes before class.